Today, we will talk about the turn coordinator. This is one of the basic flight instruments that we will find in any aircraft, and its operation is based on the gyroscopic principles. As mentioned in the video about the gyroscopic system, most of the light aircraft have the following configuration. The vacuum pump provides suction to drive the gyros of the attitude indicator and the heading indicator, while the gyro of the turn coordinator is driven by direct current from the aircraft electrical system. With this in mind, it is important to mention that this instrument comes in two main variants: the turn coordinator and the turn and slip indicator. Although both have the same principle of operation, the information they provide and the way it is presented are slightly different. Let's first look at the turn and slip indicator. This instrument indicates whether the aircraft is making a turn and how fast the heading change is occurring, which is the rate of turn. Something important to note is that this instrument does not indicate the bank angle of the aircraft, it only shows the direction of the turn and the rate of turn. Now, this instrument has another function, since it incorporates an inclinometer at the bottom, which allows to measure the quality of the turn. In other words, it allows the pilot to know if the aircraft is flying coordinated, skidding, or slipping. But before we see how it works, let's look at the parts of the turn and slip indicator. In the upper part we have the rate of turn scale with its corresponding needle. And in the lower part we have the liquid-filled capsule of the inclinometer and a solid ball which is free to move within the capsule. Let's take a closer look at the rate of turn scale and how to interpret it. Here, the center mark represents straight flight, or in other words, a rate of turn of 0 degrees per second. On the other hand, the side markings represent a rate of turn of 3 degrees per second, which in aviation corresponds to the standard rate of turn. It is mainly used in instrument flight procedures, as well as in many maneuvers. This standard rate of turn allows the aircraft to make a 360-degree turn in 2 minutes, which is specified on the instrument as we can see. Let's now see how to read this instrument by means of an example. Here, the needle is pointing the center mark, which means that the aircraft is flying straight, with a constant heading. In other words, the rate of turn is 0 degrees per second. Now, if the needle moves this way, we can see that the aircraft is turning to the right. And since the needle is pointing exactly the side mark, this means that the rate of turn is 3 degrees per second. In the same way, if the needle points the left mark, it will represent a turn to the left at 3 degrees per second. Now, if for example the needle moves to this other position, we can see that the aircraft is still turning to the left, but with a slower rate of turn, in this case, less than 3 degrees per second. And on the other hand, if the needle moves to this other position, beyond the mark, it will indicate a turn to the left with a rate of turn of more than 3 degrees per second. We have already seen how to interpret the turn indicator, now let's see how to read the inclinometer. In general terms, we can say that it allows to measure the quality of the turn. The inclinometer is the simplest instrument that we will find in an aircraft, since it consists of a capsule filled with liquid and a ball that is free to move inside. In this case, if the ball remains centered in the capsule, it will indicate a coordinated flight. If the ball moves to the side of the turn, it will indicate a slipping turn. And if the ball moves to the opposite side of the turn, it will indicate a skidding turn. For example, here we can see that the instrument indicates a turn to the right, and since the ball remains in the center, we say that the aircraft is making a coordinated turn to the right. If in this situation the ball moves to the right, which is to the side of the turn, it will be indicating a slipping turn to the right. And if the ball moves to the left, which is the opposite side of the turn, it will indicate a skidding turn to the right. Usually, in most procedures and maneuvers, the objective is to maintain a coordinated flight, so the pilot must keep the ball centered. To do so, a rule of thumb is to step on the ball, which means that in order to correct a skidding or slipping turn, the pilot must press the pedal on the side of the ball to center it. However, we will not talk about this flight technique in detail in this video. Let's see now how does this instrument work internally. The turn and slip indicator uses the principle of gyroscopic precession to measure the rate of turn. To do so, it incorporates a horizontal rate gyro, which is restricted in one of its axes. As we can see, the plane of rotation of the gyro is perpendicular to the horizon, as was the case with other instruments, such as the heading indicator. However, the difference is that this is not a free gyro. Since it has only 2 degrees of freedom, which means that it is not free to rotate on one of its axes. And if the gyro attempts to rotate in the axis that is restricted, it will precess. And measuring that precession is an excellent way to determine how fast the aircraft is changing its heading. And that is exactly what the instrument does. But let's see how it does it. Here, in the image on the left we can see the gyro from above, while on the right side we have a side view. If in this case the aircraft starts turning to the left, it would be as if we were applying a force to the gyro at this point. However, due to the precession effect, that force will be exerted at 90 degrees in the direction of rotation of the gyro, which means that it will actually be applied at this point. The result will then be that the gyro will be tilted in this way. Obviously, the faster the heading change, the greater the precession and the tilting of the gyro. And then the movement of the gyro is directly transmitted to the needle on the instrument, indicating this way the direction and the rate of turn. Clearly, the gyro will not be able to tilt beyond a certain limit, since a system of calibrated springs will limit the gyro movement and return it to its neutral position when the aircraft stops turning. This system allows to accurately measure the rate of turn and return the needle to the straight flight indication when the turn finishes. Let's see some examples of this. Here the aircraft is flying straight, so the gyro remains in the neutral position, making the needle to point the center mark. Now, if the aircraft starts turning to the right, the gyro will tilt due to precession, moving the needle of the instrument to indicate a turn to the right. This will happen as long as the aircraft continues to turn, because when the aircraft stops turning, the precession will stop and the springs will return the gyro to the neutral position, making the needle to point the center mark again, indicating a straight flight. In the same way, if the aircraft starts turning to the left, the gyro will tilt due to precession, making the needle to indicate a turn to the left with the corresponding rate of turn. This will happen until the aircraft stops turning. Then the precession will stop, and the springs will return the gyro to the neutral position. We have already seen how the turn indicator works. Let's now see the principle of operation of the inclinometer. Basically, the inclinometer consists of a ball that is free to move inside a slightly curved capsule filled with liquid. With this design, the ball will move depending on the balance between centripetal and centrifugal force during a turn. For example, if the aircraft starts turning to the right, the ball will be subjected to the centripetal and centrifugal forces generated during the turn. If these forces are equal, the ball will remain in the center of the capsule. But if there is an imbalance between these forces, the ball will move to one side or the other. This results in 3 possible situations. The first one is the coordinated turn. We say that a turn is coordinated when the centrifugal and centripetal forces are equal. Here we can see the forces acting on an aircraft during a coordinated turn. And since the centrifugal and centripetal forces are balanced, the ball of the inclinometer will remain centered. The other possible situation is the skidding turn. A skidding turn is produced when the centrifugal force is greater than the centripetal force, as we can see in this image. What will happen in this case is that the ball will move to the opposite side of the turn. For example, this aircraft is turning to the left, and the ball moves to the right. Again, this happens due to the imbalance between centrifugal and centripetal forces. The last possible situation is a slipping turn. A slipping turn is the opposite to a skidding turn. It occurs when the centrifugal force is less than the centripetal force, as we can see in this image. In this case, the ball will move to the side of the turn due to the imbalance of forces. So in this example, the aircraft is turning to the left, and the ball moves to the left. As we could see, the inclinometer is a pretty simple instrument, since it consists only in a ball that is free to move inside a capsule and therefore it does not rely on other systems to function. Let's now move on to the other variant of this instrument. The turn coordinator. The principle of operation of this instrument is almost identical to the turn and slip indicator that we have just seen. However, it has a slight difference, and it is that, when starting or finishing a turn, it also indicates how fast is the aircraft banking, not only the rate of turn. However, despite having this additional functionality, we must emphasize that this instrument does not indicate the bank angle. For that we will have to use the attitude indicator. With this being said, let's see the parts of the turn coordinator. Here, the main difference in relation to the turn and slip indicator is that instead of having a needle, we have a miniature aircraft. And therefore, the rate of turn markings are located at the sides. And as in the turn and slip indicator, at the bottom we have the inclinometer. Let's take a closer look at the rate of turn scale of this instrument. Here, the upper marks represent a rate of turn of 0 degrees per second, or in other words, straight flight. While the lower marks represent a rate of turn of 3 degrees per second, which, as with the turn and slip indicator, will allow the aircraft to make a 360-degree turn in 2 minutes. Now, an important thing to keep in mind with this instrument is that although it has a miniature aircraft, it does not provide pitch information, as stated on the instrument dial. Let's now see some examples of the operation of the turn coordinator. Here we can see that the wings of the miniature aircraft are leveled, pointing the upper marks, therefore indicating a straight flight. If the miniature aircraft now moves this way, we can see that it is inclined to the right in such a way that the wing points to the lower mark. This indicates that the aircraft is turning to the right at a rate of 3 degrees per second. The same happens if the aircraft turns to the left. In this case, the instrument is indicating a turn to the left at a rate of 3 degrees per second. Now, if for example the miniature aircraft moves to this new position, since the wing is beyond the mark, it will indicate a turn to the left at a rate of more than 3 degrees per second. And if for example it moves to this other position, it will indicate a turn to the left at a rate of less than 3 degrees per second. Having seen how to read this instrument, let's take a look at how it works internally. As with the turn and slip indicator, the turn coordinator uses the principle of gyroscopic precession to measure the rate of turn. And although it also incorporates a horizontal rate gyro, the difference is that it is tilted 30 degrees. This means that if we compare the internal mechanism of a turn and slip indicator and a turn coordinator, we will see that the gimbal of the turn coordinator is tilted 30 degrees. This inclination of the gimbal allows the gyro to also be sensitive to the banking motion, not only to the heading changes. Apart from this, both instruments are practically identical. Let's see some examples. Here the aircraft is flying straight, so the gyro remains in the neutral position, and the wings of the miniature aircraft are leveled pointing the upper marks. If the aircraft starts turning to the left, the precession caused by the heading change and the banking motion will cause the gyro to tilt this way, moving the miniature aircraft to indicate a turn to the left. This will happen as long as the aircraft continues to turn, because when the aircraft stops turning, the precession will stop and the springs will return the gyro to the neutral position, leveling the wings of the miniature aircraft. If now the aircraft starts turning to the right, the gyro will tilt to the opposite side due to precession, causing the miniature aircraft to indicate a turn to the right. And when the turn finishes, then the precession will stop and the springs will return the gyro to the neutral position. Finally, we have to mention that in the case of instruments driven by direct current, they incorporate a red flag which is visible when no power is being received, and therefore the instrument should not be used. I hope the information presented in this video was useful. If so, don't forget to share, like, subscribe, and leave a comment down below. Thanks for watching.